Hello and welcome in a new video. We will continue solving some exercises about the normal and tangential acceleration. In this exercise, we have the position vector and we need to find the acceleration vector. So let's start. The position of a particle is given by the vector r, small r, it's equal to capital R cosine omega t along I plus capital R sine omega t along j plus ct along k, where capital R, omega and c are constants. Question A, find an and at. So we have the position vector, we need to find an and at. We can start by the definition of an and at. So at, if we want to start with at is equal to dv over dt. So we need to find v. We need first to find the velocity vector, and then we need to find the magnitude of the velocity vector. So let's start to find the velocity vector. By definition, v is equal to dr over dt. So we want to derive the position vector with respect to time. And this will give, so we have r times omega times minus sine omega t. So we have this component along I, this is Vx. Now the component along y, so Vy will be equal to R omega cosine omega t. And finally Vz, it's the component of the velocity vector along k, it will be equal to c. Okay, once we found the velocity vector, we need now to find the magnitude of the velocity vector and derive it with respect to time to find the tangential acceleration. So let's write at equal dv over dt, and this is equal to d over dt of the magnitude of the velocity vector. Here we have three components of the velocity vector along I, along j and along k. So we have radical of r squared omega squared sine squared omega t plus r squared omega squared cosine squared omega t plus c squared. And this will be equal to d over dt of r squared omega squared times, we can open the parenthesis, sine squared omega t plus cosine squared omega t, which is equal to 1. And so there remains only the term r squared omega squared plus c squared. We can see that r, omega and c are independent of time because they are constants, so the derivative with respect to time is equal to 0. So at, the tangential acceleration, is equal to 0, then the acceleration will be equal to an only. So we can find the normal acceleration as an squared equal a squared minus at squared, where at squared is 0, so an is equal to a. So let's find now the acceleration vector and find its magnitude. Okay, here we had another method to find the normal acceleration. It's to write the definition of an, which is equal to v squared over the radius of curvature. But in this exercise, we don't have as a given the radius of curvature, so we cannot use an equal v squared over the radius of curvature in part A. Okay, and you can notice that the radius of curvature is required in part B, therefore we cannot use it in part A. So let's find the acceleration vector and then find its magnitude. Okay, we calculated the velocity vector, and to find the acceleration vector we have to use the definition A equal dv over dt, and we will obtain the three components of the acceleration vectors along I, j, and k. So the component along k will be 0, and finally we can get the magnitude of the acceleration vector. This is equal to r squared omega power 4 omega squared omega t plus r squared omega power 4 sine squared omega t. Another once again we have r squared omega power 4 as a common factor to cosine squared plus sine squared, which gives you 1. And so there remains only in the square root r squared omega power 4, and this will be equal to r omega squared. This means that the normal acceleration will be equal to a, and this is equal to r omega squared. In part B, they want us to find the radius of curvature. Okay, it's easy. We can use the definition of the normal acceleration. It's given by v squared over rho. We have an, we have the magnitude of the velocity vector. We can write it, we can raise it to the power of 2, and therefore we can find easily rho. So rho is equal to v squared over an. And rho will be a function of r, omega, and c. Now let's move to exercise 23. A car moves in a vertical plane on a path of equation y equal x power 3 over 60. So we have the equation of the trajectory. It's an equation that relates y and x independent of time. So the car passes by a point of abscissa xa equal 10 meters at a constant speed of 10 meters per second. We have here in this curve the variation of y as a function of x. So this is the equation of y equal x power 3 over 3. And we have a particular point A having xa equal 10 meters. They said that we have a constant speed of 10 meters per second. You have two questions. First, find the radius of curvature of its path at point A. So to find the radius of curvature, we know that the radius of curvature has two ways to be calculated. First, we can use the definition, and second, we can use the formula an equal v squared over rho. Okay, but here, since we have the equation of the trajectory, we have y as a function of x, so let's use y equal the absolute value of 1 plus dy over dx squared, and all the numerator is raised to the power of 3 over 2 over d2y over dx squared. So let's find rho in this way. So we need first to find dy over dx. We have y equal x power 3 over 60, so dy over dx is equal to 3x squared over 60. And this will be simplified to x squared over 20. Okay, so this term will be used in the numerator. Now we need to find d2y over dx squared. This is the derivative with respect to x of dy over dx. So we need to derive x squared over 20. it's equal to 2x over 20, so it's x over 10. Okay, so we have dy over dx, we have d2y over dx squared. The answer is as a function of x. And finally, to find the radius of curvature at a particular point xa, we need to replace x with 10 meters. Okay, and therefore we can find rho equal 132.6 meters. In question B, we have to determine the acceleration vector. We have to find the modulus and the direction. Okay, so they want us to find the acceleration vector. Okay, the acceleration vector is the sum of the normal acceleration plus the tangential acceleration. Since we have a constant speed, then at will be equal to 0, and the total acceleration will be just the normal acceleration. Okay, now the normal acceleration, we need to calculate. Now we need to find the magnitude of the normal acceleration, and we need to find the direction of the normal acceleration. The magnitude is easy to find. An is equal to v squared over rho. We have v at point A, and this is a constant speed, and we have just calculated the radius of curvature, and finally we can get an, it's equal to 0.75 meter per second squared. So again, a is equal to an plus at, where at is 0 because you have a constant speed, then a will be equal to an. Okay, and this is equal to 0.75 meter per second squared. Now we have to find the direction of an. If we draw a figure showing the normal acceleration, the direction of the normal acceleration, we can start calculating the angle between the x-axis and the normal acceleration. Okay, so at point A, if we draw the tangential unit vector, if we draw the vector tau, so it's a vector which is perpendicular or tangent to the path. So this is tau or t, this is tau. This is a vector tangent to the path at point A, and it's directed towards the motion, so in this direction. And we can also draw the normal unit vector. It's a vector perpendicular to tau and directed toward the center of curvature, so this is n. So we can easily draw an, it's along n, and the acceleration is along n. So we need to find the direction now of an. Okay, we need to determine, in fact, the angle between the x-axis and an. So here we have two angles. Okay, the angle between the x-axis and the an vector is equal to the sum of this small angle plus this small angle. We need to find two angles, in fact. So to find the direction of A with respect to the x-axis, we find it with respect to tau, then find the direction of tau with respect to the x-axis. Okay, so let's first find the angle between an and tau. Okay, if we write the angle figures in the cosine. The cosine of the angle figures in the expression of the scalar product between A and tau. So if we write the scalar product between A and tau, it's equal to A, the magnitude of A, times the magnitude of tau, which is equal to 1 times cosine of the angle between them. Let's call delta the angle between an and tau. So this is delta. The angle here is delta. Then we can write that cosine delta is equal to the scalar product between a and tau over the magnitude of a. Okay, let's find the scalar product between a and tau. So we have a is equal to the normal acceleration plus the tangential acceleration as vectors, and a dot tau will give us, so first we need to make an times n dot t, and scalar product t is 0 because n and t are perpendicular to each other, and there remains only one term, at times tau, scalar product with tau, so it will give us aty, because the second term will give us the magnitude of the first vector, which is at times 1, times the magnitude of the second vector times 1, times the cosine between these two vectors. The cosine of the angle between tau and tau is 0, so their cosine is equal to 1. Therefore, the numerator will be reduced to at. So cosine delta is equal to at over a. Okay, at is 0. So cosine delta will be equal to 0. Therefore, delta will be equal to 90 degrees. Okay, so I will repeat the idea. To find the angle between an and tau, this angle will be called delta. To find this angle, we used the scalar product between a and tau. Okay, if we write the scalar product between a and tau, it's equal to the magnitude of a times the magnitude of tau times cosine of delta. This will lead us to write cosine delta equal a dot t dot tau over a, and the cosine will give us a value of 0, so delta will be equal to 90 degrees. We can also use another method. It's to find the scalar product between an and tau. Simply an and tau, the scalar product is 0 because n, the normal vector, is perpendicular to tau. Therefore, the cosine between an and tau will be 0. Therefore, we can find that delta will be equal to 90 degrees. Okay, so this is another method to find delta. So we can take the scalar product between a and t, and we can also take the scalar product between an and t. Okay, t or tau, it's the same. Now we have found delta. Now let's find the angle between tau and the x-axis. Okay, let's get a use of the equation of the trajectory. In math, you know that the tangent of the angle of this angle, let's call this angle alpha. So let's call the angle between tau and x alpha. So the angle between tau and the x-axis alpha, the tangent of alpha is equal to dy over dx. Okay, this is a rule in math, and this is a slope, in fact, of the curve at a certain point. Okay, tangent alpha is equal to dy over dx, and this has been found in the previous slide. This will give x squared over 20. By replacing x with 10, with xa, we will find that tangent alpha will be equal to 5. On the calculator, we click on shift tangent. So what is the angle that has as a tangent equal to 5? We will find alpha equals 78.7 degrees. So finally, we can deduce the angle between AN and the x-axis. The angle between AN and the x-axis will be equal to delta plus alpha, which is equal to 90 degrees plus 78.7 degrees, and this will be equal to 168.7 degrees. Okay, this is an angle bigger than 90 degrees. This is in agreement with our figure.